All right, let's get right into it. We're going to pull back the curtain on this incredible hidden drama that unfolds inside your body every single day. We are talking about inflammation. And trust me, it's not just some boring medical term, it's a high stakes story of defense, alarm, and repair. I mean, it seems like a total overreaction, doesn't it? A tiny little cut, and suddenly your finger is red, puffy, and throbbing. Well, it turns out, in a way, it has been in a major battle. That little paper cut is a breach in your body's fortress, and it kicks off an absolutely amazing emergency response. So the hero of this whole story is something we call innate immunity. Think of it like your body's pre-installed factory default security system. It's the first responder, the frontline guard that's been on duty since the day you were born, and it reacts instantly, no questions asked. Okay, so before we can really get how the alarm system works, we first need to understand the fortress it's built to protect. So let's start there with our first line of defense, the body's fortress. This first line of defense is basically a series of walls and moats. Physically, you've got these tightly packed cells that act like bricks in a castle wall. Mechanically, we have ways to physically kick invaders out, like shedding skin, coughing, or sneezing. And then biochemically, we've got stuff like mucus, saliva, and even acidic sweat that create a pretty hostile environment for germs. But, as we all know, even the best fortress can be breached. And with that paper cut, the fortress wall has been broken. An invader, whether it's bacteria or just debris, is now inside. And everything, absolutely everything, now depends on sounding the alarm and sounding it fast. And here it is. Meet the alarm system, the mast cell. These guys are like sentries, stationed all throughout your tissues, especially right next to blood vessels. The moment they detect an injury or an invader, they don't hesitate. They're the ones that pull the fire alarm and kick off the entire inflammatory response. So, how does this little sentry cell actually sound the alarm? Well, it launches this brilliant two-phase attack. First, there's an immediate explosive release of chemicals it has pre-packaged and ready to go. That's called degranulation. Then it starts cooking up a second wave of signals for a more sustained long-term response. Now, the most famous of those pre-packaged chemicals is histamine. If that name sounds familiar, it's because it's the same stuff that goes haywire during an allergic reaction. But here, its job is perfectly targeted. Within seconds, it causes vasodilation, which basically means it widens the local blood vessels. Think of it like opening up all the lanes on a highway. Then it makes those highways leaky. This is the crucial part. It creates little openings so the emergency crews can get out of the bloodstream and right to the site of the injury. And this is where it all clicks. This is how the tiny things happening on a microscopic level create what you actually see and feel. That increased blood flow from the widened highways, that's the redness and the heat you feel. The leaky fluid escaping those vessels, that's what causes the swelling. And the pressure from that swelling, plus other chemical signals, causes the pain. All of a sudden, that silly paper cut makes perfect sense, right? Okay, the alarm is blaring, the roads are open, so now it's time for the cavalry to arrive. The body is calling in the heavy-hitting reinforcements. So, floating around in our blood, we have these three powerful protein systems just waiting for the signal. You've got the clotting system, which rushes in to form a physical barricade, a little mesh that stops bleeding and traps any microbes. Then, the Kinnin system shows up to help dial up the pain, which is an important signal to you and helps keep those blood vessels open. And then there's the complement system, which acts like a versatile special ops team with a few really critical jobs. The complement system has three main gigs. First, it paints the bacteria in a process called opsonization, basically tagging them to make them way more obvious and, frankly, tastier for our immune cells. Second, it lays down a chemical breadcrumb trail, that's chemotaxis, so other immune cells know exactly where to go. And finally, for some invaders, it can form something called a membrane attack complex that literally punches holes right through the bacteria, causing them to explode. Pretty cool. And following that chemical trail are the cellular first responders, our white blood cells. Thanks to those leaky vessels that histamine opened up, these cells can do something truly incredible. They literally squeeze themselves through the gaps in the vessel walls. The process is called diapedesis, and it's how they leave the highway of the bloodstream and enter the battlefield in the tissue. Two of the key players on this team are the phagocytes. These are literally the cells that eat. First on the scene, usually within 6 to 12 hours, are the neutrophils. They're like the fast-acting shock troops. They get in, devour bacteria and debris, but they don't last very long. Then, the macrophages arrive a bit later. Think of them as the heavy-duty cleanup crew. They stick around, manage the mess, and get the area ready for healing. So the backups arrived. But how do these cells actually get the job done? Let's zoom right in on the cleanup process itself. This process of cellular eating is called phagocytosis, and it's just this beautifully efficient four-step takedown. First, the phagocyte has to recognize and stick to its target. Second, it engulfs the target, pulling it completely inside itself. Third, it fuses that little bubble with another one that's packed with destructive enzymes. And finally, step 4, it just annihilates the target. Job done. And these images are just stunning. I mean, you can actually see it happening. Right here, this macrophage, colored purple, is recognizing and literally swallowing up these red blood cells. It's such a vivid look at that engulfment step we just talked about. It makes this microscopic battle feel incredibly real. So the really crucial point here is that these cells aren't just fighting invaders. They are also the sanitation department. Just like this quote says, neutrophils are essential for clearing out all the junk, all the dead cells and debris left over from the injury, which paves the way for the repair crew to come in.
Now, this whole incredible process is designed to be a short, intense, and decisive battle. But what happens when the fight just drags on and on?
This slide really lays it all out, the critical difference between acute and chronic inflammation. See, acute on the left, that's the body's ideal response. It's short, it's sharp, it resolves, and it leads to healing. But chronic on the right, that's the danger zone. It's this persistent, smoldering state where the battle just never ends. And instead of healing, this endless fight actually starts causing collateral damage to our own healthy tissues. So why does it become chronic? Well, sometimes the initial problem just won't go away. Think of a splinter you never managed to get out. But it's also the driving force behind so many major diseases, from autoimmune conditions where the body mistakenly attacks itself to things like persistent infections. In these cases, the on switch for inflammation basically gets stuck, and that turns a protective process into a really destructive one.
And that really puts it all into perspective, doesn't it? This entire complex, coordinated symphony of cells and chemicals and proteins is supposed to start, fight, win, and clean up all within about a week and a half. It's a truly amazing and efficient system when it all works the way it's supposed to.
So we're left with this really interesting duality. On one hand, inflammation is our loyal guardian, our first responder, totally essential for our survival. But when it goes wrong, it can be a saboteur, a destructive force at the root of so many chronic diseases. It makes you think, right? Learning how to direct this incredible power isn't just a scientific curiosity, it's really one of the biggest keys to the future of our health.